I'm going to introduce Leavitt path algebras, and I'll try to keep it very basic, fundamental, but feel free to interrupt if you have any questions. Okay, so let me first give the motivation here and kind of trace the history back to Leavitt, how Leavitt's name comes up here. Um, so one thing we know from our introductory linear algebra is that if we have a finite dimensional vector space or a field, right, then any two bases have the same number of elements. So what you're saying is that if K is a field, then uh, you have this isomorphism implies M equals N, right? However, the situation is different if we try to get to free modules over an arbitrary ring. So, the generalization of vector spaces is the notion of free modules in case of arbitrary rings. So if I take R to be any ring, right, then it turns out that there are many examples where you can take this um, free left module, and you can see this will be isomorphic to this one, uh, whereas M can be different from N, right? Now, if you have the situation that this forces M to be equal to N, then we say this ring has invariant basis number property. So in about 1950s, Bill Leavitt introduced a mechanism to produce rings which will defy invariant basis number. Okay, here is one quick way to see it. So if R is a ring, and we have these x1 through xm, y1 through yn. Let's keep the same thing, xn and yn. These are generators with the property that if we take yi xj, this is delta ij, right? And summation xi yi equals 1, then in that case, so this is an exercise for you. You can check that this will be isomorphic to this. So you have two free left modules defying the invariant basis number, right? So it turns out that there is a nice quotient of path algebra that gives examples of rings with this property, okay? And that's why the name Leavitt comes in this. So let me now formally introduce what Leavitt path algebras are. So a bit of terminology here. So when I say E is a directed graph, I am giving the following data. So directed graph means I'll have some vertices, okay? So E naught will be the set of vertices, and then I'll use E1 for the set of edges, right? So I have E naught, I have this set E1, and then I have two functions which I'll associate the edges with. So S and R, these are functions from E1 to E0. Okay, so S of E means the source of edge E, okay, and R of E means the range of edge E. So for example, if E is this edge from A to B, right, then I'll say source of E is A and range of E is B, okay. So throughout this talk, when I say E is a directed graph, I mean that you have this. A directed graph means you have a graph where the edges have a sense of direction. We also use the word quiver for that. So some of you may be using the word quiver. So we have vertices, we have edges, and we have a notion of source and range of an edge. Okay. Now, let K be a field the Leavitt path algebra uh, of a directed graph E is a K algebra generated by vertices, edges, and what we call ghost edges, and I'll explain what I mean by ghost edge. So V is in E0, E is in E1, and let's say E star is in E1 star. So let me first mention what. So for every edge, so if E is an edge like here from A to B, we'll consider the edge going backward. So let me just try here. So we will imagine this edge going backwards, and we will call it ghost edge, and we'll denote it by E star. So it is not there, but we are imagining, that's why the name ghost edge. Okay. So E star is ghost edge for E. So for every edge E, there is a corresponding ghost edge. Now it's quite clear that source of E star would be same as range of E, right? And range of E star would be same as source of E, right? As you can see here, since E star is going back, source of E star is B, which is the range of E, right? Okay, so now the Leavitt path algebra is a K algebra generated by these vertices, edges, and the ghost edges, subject to the following relations. So first is that these vertices are orthogonal idempotents. So what do we mean by that? If we take vi square, that is vi, and if you take any two different v sub I and v sub j, you get 0 here. So if I is different from Okay, so that means the vertices are orthogonal idempotents. Second thing we want is that if you take an edge E and you multiply with the source of E, okay, that would be just E, and this would be same as if you take E and multiply with the range of E. That's quite natural. So um, this is just to make sure that we have this the path algebra structure. Okay. Third, same thing for ghost edges. So we have E star. Now source of E star is range of E. So I'll write like this. Is same as E star, and then range of E star, which is source of E. Right? Okay. And then we have fourth and fifth condition, which are called Kuhn-Krieger conditions. So let me first write CK1, and I'll explain a little bit of history of these conditions as well. So what is CK1? CK1 condition is that if you take E star E, that will be range of E. Okay, and if you take two different edges, E and F, then E star F would be 0. Okay, so here if E is different, okay, what is going on? So there is a time lag between. Yeah, so E star E equals range of E, and if you have two different edges E and F, then E star F equals 0. And Kuhn-Krieger 2, CK2 condition is if V is a regular vertex. What does that mean? So regular vertex means it emits at least one edge. So that means it is not a sink. Okay. So in graph theory, most of the terminology, the choice of words is self-explanatory. Sink means what? So you have a vertex where all the edges get into this, but no edge gets out of it, right? So it doesn't emit any edge, so you call this a sink. Okay, so a regular vertex means it is not a sink. Okay, so it emits at least one edge, and it is not an infinite emitter, so it doesn't emit infinitely many edges. Okay, so if V is a regular vertex, that means V is not a sink, and it is not an infinite meter. Okay, then V equals sum of E star, where what are these edges E? Well, these are E such that source of E equals V. Okay, so these are all the relations that we demand. So what is a Leavitt path algebra? Over a directed graph E? Well, it's an algebra, it's a K algebra generated by vertices, edges, ghost edges, subject to these 5 relations, where first 3 basically give you the usual path algebra structure, and then you have these 2 extra conditions. Now, these CK conditions, so CK is actually short for Kuhn-Krieger. So let me just take a small detour here and explain to you what is the connection of these 2 graph C star algebra. So this comes from functional analysis, especially this graph C star algebra. So what happens there? So these two conditions were introduced. If you have a Hilbert space and you have orthogonal projections. Okay, so you have a directed graph, and then you are considering these orthogonal projections in the C star algebra that you get out of that, and then you have these partial isometries. Okay, then these conditions read there. So originally these conditions were introduced there in the context of graph C star algebras in the following way. So CK1 means S E star SE equals the orthogonal projection on range of E. Okay, and CK2 in the theory of graph C star algebras reads as if you have again V is a regular vertex, then P of V, so the orthogonal projection on and that vertex is sum of E star. So these are orthogonal projections, and these are partial isometries. Right? So partial isometry means what? So remember, if you have x is called partial isometry. If you look at y equals x star x, that is a self-adjoint idempotent. So y star equals y, and y square equals y, right? So that's the connection of these conditions. So you can see it's just the same thing, right? Okay. Now let's see in some concrete examples what these things are. So let's do things a little slowly so that you understand. And please ask questions if you have any. So examples. Let's take a very basic case. Okay. And what happened here? Okay, so I have, let's say, two vertices, say V1 and V2, and there is an edge E, and the arrow is V1 to V2. Okay, let's see what will be Leavitt path algebra for this directed graph. Okay, so well, so we have the generators are V1, V2, right? Then E, and then we have E star, right? And we have the conditions. Remember that V1 square is V1, V2 square is V2, V1 V2 or V2 V1, they're 0. Also you have V E equals E, V1 actually equals E V2, right? Same thing for E star. You have E star, V2, E star equals E star V1, and we have V1 is the source of E, so we have V1 equals E star, and E star E equals range of E, which is V2. Okay, now it's not too difficult to see that this algebra that we are getting here is isomorphic to to 2 by 2 matrix ring over field K, with a very usual map here. So we can associate V1 to to 1 0 0 0, right? V2 to 0 0 0 1, E to 0 1 0 0, and E star to 0 0 1 0. Now, in fact, you can check all these things will hold here. We can generalize this idea and see that if we had a Dinkin diagram of type A sub n, which means if you have this kind of directed graph, so you have V1 to V2, V2 to V3, all the way to Vn, here is Vn minus 1, right? Then the Leavitt path algebra for this graph would be isomorphic to M and K, right? Under this map, so you can just map V sub I to let's write the matrix units. So Eij means I'm putting 1 at ijth spot and 0 elsewhere, right? So let's map V sub I to Eii, and suppose these are, so this is E1, this is E2, and so on. So I can map Ei to Ei plus 1, and the ghost edges Ei star to Ei plus 1 I. Clear to everyone? Please ask questions if it's not clear. So now one can actually see that you can have non-isomorphic directed graphs which will give you same Leavitt path algebra. For example, now you have this graph which gives as Leavitt path algebra this matrix ring or field K. Now you could also take another graph. Let's keep it example 3 here. So suppose I take a vertex V, and then I have a bunch of edges getting into this, and so on. So say W sub n minus 1, I have E1, E2, E3, all the way to En minus 1, all these going in. This is an exercise for you. You can check that in this case also the Leavitt path algebra would be isomorphic to, in fact, here is another one. You take two vertices, V and W, and you put these edges. So suppose I have these n edges. In this case also you'll have, well, n minus 1. So if you have E1, E2, all the way to E sub n minus 1, this one is also. So you have, right here, you have 3 different directed graphs. They're all non-isomorphic. Well, to see that they are non-isomorphic, it's very easy. You can see here for this vertex, there are n-1 edges getting into this. So if you take the two different types of degrees, in degree and out degree, the in degree of this is like the incoming edges, those are n-1. However, in this graph, the directed graph right above that, there is no vertex with the,
Hello,
the
sir.
incoming. Yeah.
Yeah, sir. Will this symmetric group will come to any help like symmetric? If I take this relations of these vertices and edges, it actually we can actually connect it to some symmetric group elements and get the matrix representation for that. Is that possible to get some representation for this kind of path algebras using that? Like what I'm saying is.
Yeah, well, so I'll take one special case, and I'll show that. Um, so yeah, for example, if you want to construct automorphism group, then yeah, I'll get to that. So you can actually look at the semi-direct product of the automorphism group, and some symmetric group comes in picture. But in general, the representation.
Sir, what I get is that anyway we are actually defining some function on this connection between edges and vertices, right? In some way that actually connects to some like some mappings to symmetric group of that many edges and vertices. Like I think I like, is it possible? That's a simple like.
Yeah, and I have difficulty understanding your question, but uh, I don't understand what you mean by
So what I'm saying is that
adjacent
you,
vertices. You see,
yeah.
the edges. See, the usual multiplication is just the concatenation of path. That's what you do in any path algebra. You when so small things that you could actually see in between the lines here is that when you multiply things, there is the usual concatenation of paths. So suppose I take this edge here, right? And and then the next one starts where this one ends. So then I can multiply, and I get a path, right? But if things are not compatible, then they multiply to zero. And in fact, right there, there is a small exercise for you to see that. You can say, oh, you told us how to multiply two vertices, you told us how to multiply edges in a very particular way, like E star E, um, and an edge with its source, or but what happens if I take any two different edges, how to multiply them? Well, it's hidden right here. If you take two edges, how would you multiply? Well, in view of what I just wrote, you could say, well, I will see this as E, and then I'll use number 2 there, see range of E, right? And then F, I will see a source of F, and then F. And right here, now I have two vertices. I know how to multiply two vertices. So if these were same, then that is an idempotent. If they're different, it goes to 0, right? So what does that tell us? This being equal to this means what? Range of E is equal to source of F means E and F are adjacent. So then you have the usual concatenation. So this survives. Otherwise, this product will go to 0, right? Also, if you take any vertex and you multiply with any edge, here I told you how to multiply an edge with its source, or how to multiply an edge with its range. But suppose you say, oh, but you didn't say anything about an arbitrary vertex and an edge. Well, again, you can play the same game. You can say this V is source of E and then E. Now you have here product of two vertices. You know what to do there in view of what I just wrote, right? So once I give you these 5 conditions, then you know how to multiply anything there. Um, Now, hold on to your question. Maybe at the end, you can again tell me what are you trying to ask. So is this part clear to everyone, that we can have completely different directed graphs and we can get the same Leavitt path algebra? One thing which I should also mention here is that this Leavitt path algebra is universal with respect to this kind of relation. What do I mean by that? So let me mention the universal property of Leavitt path algebra. So by universal property there I mean the following. If A is any K algebra, and let's keep an eye on time. Okay, so it's 11 o'clock in night here. So that means 9:30 in India. So if A is any K algebra containing generators, let's say A, V, B sub E, C, E star, where V is in E naught, E is in E1, and E star is in E1 star, subject to those relations, so satisfying that if you take a VAW, that is delta VWAV, and well, all the things that I wanted, that you have BE and then A SE equals BE, BE A range of E. Same thing for CE star, CE star, and then A range of E equals CE star equals CE star, A source of E, and what else we want? CE star CE equals A range of E, and well, if V is a regular vertex, we want this to hold, right? Then what is happening? I can't write now. Yeah. Okay, so it seems I'm writing faster than what my Apple Pencil can process. Then there is K algebra homomorphism phi from this Leavitt path algebra to A, such that P of V equals AV, P of E equals BE, and phi of E star equals C star. So this is what I mean by the universal property with respect to those defining relations. If you have any K algebra with those generators satisfying same kind of relations, then you have this key algebra homomorphism between Leavitt path algebra and this algebra. Okay. Now let's take some more examples. Here is another interesting example. Suppose I take a vertex and I take a loop at that. So we have a vertex V and we have an edge E connecting V to V itself. Well, of course, then the ghost edge will also connect V to V, right? Then can anyone in audience tell me what will be Leavitt path algebra of this directed graph? Does it look familiar to you? Any algebra that you know of? Anyone? And I see no response. So, well, this is isomorphic to Laurent polynomial algebra. So, Kx inverse. That's not too difficult because you see, you can associate V to 1, E to X, and E star to X inverse. And you can see this algebra isomorphism here. Another example, and this will give you an example of the ring with ring defying invariant basis number property. So non-IBM ring is if you take a vertex, we call it rose graph. So think of several petals on it. So you have a loop here and a loop here and so on. So suppose you have these n loops on this vertex V, right? So you have E1, E2, all the way to En. Then, of course, you have, if you read the Kuhn-Krieger condition here, then any I star, E sub I, is a range of E sub I, which is V, right? And if you look at V, then this is E1 star plus E2 star all the way to En star. If you go up, you can see that this is precisely what I had said here. So we are in that situation, right? And so this one here, if you denote this Leavitt path algebra by L, then you have L as a module over itself is isomorphic to n copies of L, right? So this is an example of ring with non-IBM. Let me give you one more example before I move on to some properties of Leavitt path algebras. So let's take a vertex here U and an edge from U to V, okay, and then a loop here. Call this E, call this F. Okay. Let me ask this one. Can anyone in the audience guess what kind of algebra we will get here? Well, it's late in night here, but you shouldn't be sleeping. Are people awake? I see no response. Okay.
Sir,
Mhm.
sir, is it the direct sum of the this Lorentz polynomial algebra and the M2 of R kind of? So M2 of
Uh,
K kind of.
okay, so you're close. You're close. So you said, in fact, one can see this is isomorphic. Okay, as left ideals, yes, it will be isomorphic to kx inverse cross the infinite matrix ring with. So this means there are only finitely many entries in any row. But more precisely, this is just this algebra. This is generated by two variables x and y, such that xy equals 1. So this is a prototype example of a ring which is not directly finite, right? So you have this um, generated by x and y, where xy equals 1, but yx is not 1. To see this, well, let's first take x to be e plus f, okay, and let's take y to be e star plus f star. Then what will be xy? Well, xy would be, so let's do things slowly. We have e plus f, we have e star plus f star. So this is e star plus e f star plus f e star plus f f star. Right. Now, we have okay. Now let me first write this also, and then I'll get to what is that. So yx would be e star plus f star, e plus f. So this will be e star e plus e star f plus f star e plus f star f. Now e star e is range of e star f is 0, right? F star e is 0, and f star f is range of f. Range of e is u, and range of f is v. Now, it's not too difficult to see that if you have E a finite directed graph, okay, so if E is finite, finite means what? That means E naught is finite, right? Finite graph really means that the number of vertices is finite, okay? So in that case, Leavitt path algebra over E is a unital ring, okay? then Leavitt path algebra has identity element, and not too surprisingly, that identity element 1 is just the sum of all the vertices. That is not too difficult to check. If you have the number of vertices is finite, just take the sum of all the vertices. That will be an identity element for that Leavitt path algebra. Otherwise, it is a ring with local units, in the sense that if you take any finite number of elements, then there is something that acts as identity on those elements. Okay. Now here, this u plus v is then the identity element. So yx is 1, right? However, if you look at xy, so now let's look at the EE star plus FF star. Can you tell me what will be EE star plus FF star? Anyone? What will be EE star plus FF star?
V plus U, sir.
EE star plus FF star would be? What did you say?
V plus U.
Not V plus U, but just U. That's the CK1 condition, right? I mean CK2 condition. U is a regular vertex, and so if you read CK2 condition, it says U equals the sum of EE star, where source of E is U. What is source of E? U. What is source of F? U, right? So EE star plus FF star is U. Now look at EF star. Well, EF star, you can see you have E, then a range of E you could put here, and then source of F star you can put here, and then F, right? Range of E is U, source of F star would be V. So this goes to 0. Same thing here, right? So what do we have? We have, let me just block this. So I have xy is U, and yx is 1, right? So xy is not 1. So this is different from 1, as you can see. 1 is U plus V, right? So now I want to convince you that this Leavitt path algebra is actually isomorphic to this Toeplitz algebra, the algebra freely generated by x and y with just one condition, x y equals 1, right? So just send well, I wrote there x y equals 1, so I'll send y to this capital X, and x to capital Y, right? And so let's call this phi. And we also have by the universal property, the other map, because you see, if we take these generators, so let's take, I have what, xy equals 1 I took, right? So if I take yx, 1 minus yx, then y square x, y minus y square x, and yx square, x minus yx square. You can check that, first of all, this is we have a nice system of relations and with these generators, because you see these are uh, orthogonal to each other. Yx multiply with 1 minus yx, you will see under the, keep in mind xy equals 1, right? So if you multiply yx with 1 minus yx, what would you get? You will get yx minus yxyx. Now remember xy is 1, so this is 0, right? So we'll have all those relations. So universal property tells us that we'll have a K algebra homomorphism with the property that, let's call that psi. So psi of u would be yx, psi of v would be 1 minus yx, psi of e would be y square x, psi of f would be y minus y square x, and psi of e star would be yx squared, psi of f star would be x minus yx squared. Okay, and then one can check that these are inverses of each other. Okay, and so you have this isomorphism, algebra isomorphism between the Leavitt path algebra and this. Okay, let's see. And I am already feeling sleepy, but let me just mention a little bit about the ideal theory here. So now, by now you have seen that there is this high degree of non-commutativity here, right? It matters how you are multiplying. You just take two edges, I mean one edge and ghost edge, and you have seen that E star E and E star are two completely different things, right? So this is a non-commutative ring. However, the ideals behave in a very nice way. This whole multiplicative ideal theory is very much like in the case of commutative rings. Now, in order to comment about those, let me just introduce a few simple terminologies, and then I'll mention some very interesting results about ideals. So first of all, again, suppose E is a directed graph, okay? Then we use the word hereditary for a subset H of E naught. So what do we mean by that? So H is called hereditary. If anytime a vertex V is in H, that implies that any vertex for which there is a path from V to W is also so. Well, let's write like this. So if V is in H, and if there is a path from V to W, let's use this symbol to denote that there is a path from V to W, then W is in H as well. And that's why the word hereditary. So if a vertex is there, then any vertex with a path from V to that is in H as well. Okay. In other words, if a vertex V is in H, then the tree out of that vertex is contained in H. That's what hereditary means. Okay. And H is called saturated. if any regular vertex, so again, regular means it is not a sink, it is not an infinite emitter. If we have that R inverse, range of S inverse of V, if that is in H, that implies V is in H. What does that mean? So in plain English, we are saying any vertex which feeds completely into H is also already in H. Okay, so if there is a vertex, a regular vertex, from which every edge that goes out that is inside H, then that vertex must be in H as well. Okay, so that's what saturated means. Now, if you have a, well, first of all, it's not too difficult to see that if you take any two-sided ideal, okay, so if I is a two-sided ideal of Leavitt path algebra over E, then I intersection E naught is a hereditary saturated subset of E naught. The proof is quite straightforward. If you want to see why it is hereditary, take any V in I intersection E naught, okay, and suppose we have a path from V to W, right? So showing hereditary means we need to show that W is in this I intersection E naught as well. Well, so there is a path, so there is some alpha whose source, so source of a path, if you have a path consisting of these adjacent edges, this we will call source, and the endpoint will call range of the path. So source of alpha is V, range of alpha is W, right? So range of alpha I meant. So if you look at alpha star alpha, well, that's W, right? And you could write this alpha star V alpha. Now V is in ideal I. It's a two-sided ideal. So you multiply by ring element in left or right. You fall back inside the ideal, right? So this will be again in I. W is of course a vertex. So that means W is in I intersection E naught. So that shows it is hereditary. To see that it is saturated, take any regular vertex V, okay, and suppose that the range of S inverse of V is contained in I intersection E naught. Showing it is saturated means what? We need to show that V must be in this set I intersection E naught as well. Now remember Kuhn-Krieger two condition. V is sum of E star, source of E equals V, right? So source of E is V, so that means if you put here range of E, right, then this is in I. Again, you have a two-sided ideal. You multiply by using elements in left and right. You fall back again in I, right? So that means V is in I, and it's a vertex, so it is an I intersection E naught. So we are done. So that shows if I is a two-sided ideal, then I intersection E naught is a hereditary saturated set. Now, it turns out that Leavitt path algebra is a graded ring. in a very usual way. I mean, just take the grading in the following way. So take degree of any vertex to be 0, degree of edge to be 1, and degree of E star to be -1, right? So if you remember how we multiply elements in Leavitt path algebra, it's quite clear that any monomial will be of the form, so you have the field element, then you will have a path and a ghost path, right? That's how any monomial will look like. So then we can see L as great sum of Ln, where what will be L sub n? These will be those elements where the degree of alpha I minus degree of beta I would be n. So you have length of path, and then the length of ghost path you will subtract, and when the difference is n, then you put that as homogeneous element, right? So that gives a very natural grading on Leavitt path algebras. So so we can talk about graded ideals here. So an ideal I here is called graded if I is of the form I. So think of this as now the graded ideals have a very nice structure. It turns out that any graded ideal is generated by some special type of idempotents. And for that, let me just introduce one more quick term here. So suppose I have a hereditary saturated set H. So H is a hereditary saturated subset, okay? Then an infinite emitter V in E naught without H is called a breaking vertex if the cardinality of this S inverse V intersect R inverse E naught without H is finite, okay, at least one, and it is finite. So then we denote the set of all breaking vertices by B sub H, and anytime if V is in B sub H, I'll use this symbol V sub superscript H to denote this kind of element, V minus E star, source of E equals V, okay, and range of E is not in H. Then it turns out that any graded ideal is of the form IHS, where this is an ideal generated by H union this V to the H, where V is in S, and not just that every graded ideal is generated by is of this form. The quotient with these ideals give us again a Leavitt path algebra. So if you mod out this Leavitt path algebra by such graded ideals, it turns out this is Leavitt path algebra over a new graph which we call the quotient graph. So E mod HS. What is this quotient graph? Well, this quotient graph, so E mod HS is a graph where the vertices are E naught without H, union for any V in breaking vertex without S, you put a V prime, okay? And okay, so this is a lot of work very quickly, but not too difficult. If you sit quietly and you try to construct, you will easily see how to construct quotient graph. So here we put all the edges E in E1 such that range of E is not in H. And then for every E in E1 with range of E in breaking vertices without S, we put corresponding E prime, okay? And we very naturally extend R and S. So source of E prime is just source of E, and range of E prime is prime of range of E, okay? With this, we get this quotient graph, and it turns out that this factor group of this factor ring, the quotient ring of Leavitt path algebra, modulo this graded ideal, it's a two-sided ideal, is Leavitt path algebra over this kind of graph. Also, this graded ideal itself can be viewed as Leavitt path algebra over some other graph. I'm not going to get into this F, but one can see this special kind of subgraph. And the non-graded ideals have a slightly difficult structure. And I'm kind of now tired, sleepy actually. But yeah, I can just quickly mention that if you take non-graded ideal, then that looks like, so so if you take any two-sided ideal, that will have this kind of structure. So IHS plus you have this ideal, the other part which is generated by I'm writing F sub T, C sub T. So let me just see. These are cycles. So C sub T is a cycle without exits. In the quotient graph, right? And this is a polynomial with non-zero constant term. Now, as I mentioned, the ideals have very interesting property of commutativity. So if you take two ideals, A and B, of Leavitt path algebra, and one of them is graded, suppose A is graded, then it turns out that AB equals BA. Okay. And the reason why this turns out to be same, AB and BA, is because you can actually prove that AB is same as A intersection B. And so since intersection A intersection B is same as B intersection A, it's not surprising that you get AB equals BA. Also, and this is something that my PhD student together with Ranga Swami, she proved that just the way you have, so one thing that you learn sometime in high school or even before that is that you have two integers, say m and n, right? Then the least common multiple of m and n multiplied to greatest common divisor is the product of m and n, right? So for proper domains, the special kind of commutative rings, the analog is that if you take two ideals, then A intersection B multiplied to A plus B is AB, right? And it turns out that here it is true. In case of Leavitt path algebras, if you take two two-sided ideals A and B, then you have this very interesting identity. Also, there is this whole theory of prime ideals, and a lot of things you can do. If any of you is interested, you can actually see. If you go to my webpage, you can see. Recently, with my graduate students, we generalized many things that are known for commutative rings, like irreducible ideals, strongly irreducible ideals, and strongly prime ideals. So a lot of theory of ideals which is known for commutative rings uh, can be actually seen to behave very nicely in case of Leavitt path algebras as well. All right, let me stop here.